Evening everyone, and welcome to our live stream for our second chemistry paper. So obviously what we're going to do today is go through all of the work that is in C4, C5 and C6. But to make it a little bit easy for those of you doing combined science, what we're going to do is go through all of the combined work first of all, and that's also on those of you doing the GCSE chemistry paper. And then what we're going to do is just do the bits that are only on the GCSE chemistry for those of you doing the triple science. So we'll do all of the stuff for everyone first of all, and then we'll go back just to revisit any of the triple only work later on. So we do have the chat going on down there. We shall see whether it will make it to the physics one or not, because if we're going to have lots of silly comments, then I'll just bin it off for the next one for the physics. Obviously, if there are any things that we're going through that you're not sure on, then do post it in the chat. I'll try and keep an eye on that one as we're going through. May not answer instantly, but I will try and get through any of your questions that you do ask at the same time. Right, hopefully we're going to be done by 8 o'clock. I will do my best to stick to the 2 hours. Biology overran by 10 minutes. We're going to try to keep this one within the 2 hours. So first up then is C4. Now, the first thing we had a look at in C4 were some of those key groups from the periodic table. So the first group that we looked at were the alkali metals, which are in group 1. So hopefully you remember on the periodic table, the far left-hand side, that's where we find group 1. Now, what we find with those group 1 metals is that they're incredibly reactive metals, particularly with the oxygen and the water that we find within the air itself. So when you saw, and hopefully you saw this demonstration where the alkali metals were dropped into water, then what you actually find is that they're stored in oil. So they're not just stored in a jar with air, because otherwise they would react with the oxygen and the water in the air. We store them in oil in those jars to stop that reaction occurring. What we do find though is because they are metals, then they do have some of the typical properties of metals. So when we cut them, then they're nice and shiny. They're good conductors of electricity, they're solids at room temperature. So all those typical properties of metals as you would expect. Now, the other things we need to know about are the trends as you go down the group itself. So a few trends you should remember here. First of all is they're softer as you go further down, so it means they're easier to cut. So the first one, lithium, a little bit tricky to cut, but by the time you're getting down to potassium, it's just like slicing a bit of cream cheese, to be perfectly honest. The density will increase the further down the group you go, and the melting point will decrease. Now, as I said, one of the demonstrations that your teacher hopefully gave you was looking at the alkali metals when you drop them into a big sort of tank of water. Now, you should have seen lithium, sodium, and potassium in that case. So what we actually find there is lithium is the really dull and boring sort of one that just fizzed around on the surface really slowly. So that's the one we kind of put in first just to make you realise that not everything in chemistry is overly exciting. Second one would have been the sodium. So that's the one that as soon as it touched the water turned into a molten ball, so literally turned to liquid, and then it zips around on the surface quite quickly as it fizzed. Third one was potassium, which as soon as it touched the water, it burst into fire and it burns with that lilac flame, and it's moving really quickly on the surface, fizzing lots, and in some cases can actually explode as well, particularly if you tend to amp up the bit you put in, so it's a little bit bigger and more exciting. Now, when we're looking at our alkali metals and the reaction with water, then the good news is if you learn the general word equation, then what you're going to find is that you've just got to change the name metal for whatever the metal is, and then you've got it right every single time. So the general word equation that we've got is metal plus water makes the metal hydroxide and hydrogen. So in order to get it right each time, all you have to do is just change the word metal for whichever metal it is. So if it was lithium, it would be lithium plus water makes lithium hydroxide plus hydrogen. If it was sodium, sodium plus water makes sodium hydroxide plus hydrogen. Dead easy. In terms of the balanced symbol equation for this one, again, this is one of the nice balancings because you've just got to learn a rule. So as soon as you've written the symbol equation, then all you need to do is stick 2's in front of everything except for the hydrogen. So 2 in front of your metal, 2 in front of the water, and 2 in front of the metal hydroxide. And that just means that you've got your balancing right without technically having to know how to balance an equation, which is quite nice. When we consider the group 1, then hopefully we remember if they're in group 1 of the periodic table, they have 1 electron in their outer shell. So what we actually find is that as you go down the group, then we have more of those electron shells that hopefully we remember from our paper 1 work. Now, what we find, the reactivity of these, as we go down the group, will increase. And that's because the more shells we've got, then the further from the nucleus that outer shell electron actually is. And therefore, there's less of a pull, so it's more easily lost, and therefore more reactive. So all we need to do is, if it asks you to explain why the group 1 actual metals get more reactive the further down the group we go, all you need to say is that the outer shell electron is further from the nucleus, and therefore it's lost more easily. The next group you looked at were the halogens, which are group 7 on the right-hand side of the periodic table. So group 7, the halogens, key point about these is they're what's called diatomic. Okay, di meaning 2, atomic, atoms. So when we're looking at them and we're writing any of these halogens in their formulas, you've got to remember the little 2 at the bottom. So what we actually find is, if you don't remember that one fact, any balancing equation that involves a halogen is wrong. You're going to get nothing, because your formulas are going to be wrong and your balancing will be wrong as a result. So anytime you're writing fluorine, chlorine, iodine, astatine, bromine, any of those, always the little 2 in the bottom right, because they go around as the 2 join together. So one of the things we do need to know about these is their state at room temperature, and also the colors that they are. So if we start at the top of our group 7, we've got fluorine, which is a gas at room temperature, and it's pale yellow in color. Chlorine, next one down, still a gas, but it's green in color. Third one is bromine, which is the only liquid there, and it's orange in color. Iodine is a solid and grey, and astatine also solid, but a dark grey black colour. So what we can see is, as you go down that group, they go from gas at the top down to solids, and they go from the pale yellow colour all the way down to the dark grey black colour. So they're getting darker the further down you go. What we're also able to work out from this is the fact that the boiling and melting points are increasing the further down you go, because obviously if they're going from a gas at the top down to a solid, it's a given that they increase too. Density will also increase the further down the group you go, just bear that one in mind. Because these are non-metals, then there's a couple of key properties we should remember. They're brittle when they're solid, and they're poor electrical conductors. In terms of the reactions of group 7, then the first reaction we need to know about is that when they react with our actual sort of metals and so forth, then they're going to produce something called a salt. And when we're writing these, we need to know our general word equation, which is metal plus halogen makes something called a metal halide. Now, the key thing here are the endings. So when we've got our metal and our halogen, then our halogens all end in INE. So chlorine, bromine, iodine, INE is the ending there. But when they're in their salt, it always ends in IDE. So rather than writing something like sodium chlorine, wrong, you have to write sodium chloride. So make sure you remember that subtle change to the ending in order to get the mark on this one. When we come to actually write the balance symbol equation, again, remember that all-important bit that we are going to require our halogen to be as the diatomic molecule. So this is obviously just the formulas. So we've got our metal, which in this case is sodium, chlorine, always diatomic, the little 2, and we're making sodium chloride. In order to balance it, all you need to do is a 2 in front of the metal and a 2 in front of your metal halide. Nice and simple, as long as you remember the diatomic part. So when we're actually looking at the reactivity of our halogens then, and again, we go down the group as we do this, then what we find is the reactivity decreases the further down the group you go. So it's the opposite of our group 1. And the reason for that is that in group 7, hopefully remember there are 7 electrons in the outer shell. And the same thing happens. The further down you go, the further out the outer shell electrons actually are from the nucleus. In this case, though, they're trying to gain that last electron. So if they're further from the nucleus, that force of attraction is therefore weaker, and therefore it's harder to gain that last electron. So they're less reactive. Do remember that when they actually gain that electron, then they become an ion with a single negative charge. So if ever you're looking at the actual ions for these, then it will just have the single negative charge in the top right. And that's going to be useful if they're asking you to work out the formulas of any particular ionic compound involving a halogen. Another reaction we looked at to do with the halogens are the halogen displacement reactions. Now, we use the word halide here, which is just a compound of a halogen and one other element, which is usually a metal or something like hydrogen here. And in our displacement reactions, what we're actually looking at is a more reactive halogen is going to take the place of a less reactive halogen that's joined to something else. So if you've got chlorine on its own, and we've got sodium bromide, for example, as a compound, then because chlorine is more reactive than bromine, it takes the place of bromine. So we would then end up with sodium chloride and then bromine on its own. So just remember that displacement reactions, the more reactive halogen displaces the less reactive halogen from its salt, the halide. Those of you doing the higher tier, you do need to know about half equations to model things like our displacement reactions. So what we're actually looking at in a half equation is something that's happening to just one of our reactants. So in this case, if we were looking at our reaction of chlorine and bromine in this displacement reaction, then one of our half equations would be focused purely on chlorine. So you've got your chlorine gas, and what's going to happen is each chlorine is going to gain an electron, hence we've got 2 electrons, E minus the symbol there, and we make 2 chloride ions. So that's one of the half equations, and your other one then is for your bromine, and what we're going to find here is that we are going to make this. So we start off with our bromide ions because they're joined up obviously to our metal. And then we're going to form bromine gas, Br2, always remember the 2, and 2 electrons are going to be moved at that point too. And hopefully we remember a little bit about reduction and oxidation. So reduction, if we're thinking about oil rig, okay, then reduction is the gain of electrons. So in this case, chlorine is being reduced because it's gaining electrons, whereas the bromine is losing electrons, therefore it's oxidation. So remember, oxidation is the loss of electrons, reduction is the gain of electrons. Back for everyone again now, so foundation and higher. Then we need to know about the noble gases. So noble gases are the ones on the very, very far right in group 0 on the periodic table. So helium, neon, argon, krypton, xenon, and radon, those are the noble gases. And we call them the noble gases because they're pretty unreactive. Okay, they don't really take part in many chemical reactions at all. And that's also why it took us quite a while to actually discover that they even existed. Now, the key things about our noble gases, as their position on the far right of the periodic table suggests, is they're nonmetals first of all. Secondly, the name does have it that they are gases at room temperature, and they've got a full outer shell of electrons, hence why they're unreactive at that point. As they've got that full outer shell of electrons, they go around as what's called monatomic molecules, so just single atoms, and they've got these weak forces of attraction between them. And because they've got weak forces of attraction between them, then they've got low boiling points, and therefore they're gases at room temperature. Again, we need to know our little trends as we go down our group. So as we go down group 0, then the attractive forces between the atoms get stronger. Their boiling point will increase as a result of that, and they also have an increase in density. Now, one of the things that we've talked about are obviously these trends in terms of boiling points, densities, and melting points, and so forth. And one of the key things to remember here is that they could give you a graph or a table with the information about a number of the halogens or the alkali metals or the noble gases, and they'll ask you to fill in some missing bits. Now, because we know the trend, and you can see that when you look at the table or the graph, then you need to work out the differences between the others and then apply that to work out the missing one. Don't literally look at it and think, oh, well, they've given me minus 108 and minus 186, so I'm just going to go smack bang in the middle. Actually work out the differences between them, because the range they will give you as a correct answer is relatively small. So do work out the differences between the others that they've given you and apply that to your missing one. Last thing we really need to think about in terms of the different groups on our periodic table is about the reactivity of these elements. And one of the key things we looked at here were the reactions of the metals. So hopefully we remember that metals form positive ions, and that the more easily a metal will form an ion, then the more reactive the metal actually is. So what we actually find here is that a metal can react with water or acids if the metal itself is more reactive than hydrogen, because obviously water and acids both have hydrogen in them, and that's what's actually carrying out the reaction. So as long as the metal is more reactive than hydrogen, we get a reaction with either water or an acid. And what we find in terms of the general equation for our metal and our water is that we will make a metal hydroxide and hydrogen. If we look at the metal and acid, we make a salt and hydrogen. So just remember, obviously, the fact that we've got those two general word equations. All you need to do is change the word metal for obviously which metal it is. And to work out the name of your salt, what we do is the first word is your metal, and the second word of your salt name comes from the acid. So hydrochloric acid makes a chloride, sulfuric acid makes a sulfate, phosphoric acid makes a phosphate, and nitric acid makes a nitrate. In any of these reactions we're talking about where we're making a gas, so where we're making hydrogen, whether it's the metal and the acid or the metal and water, then what we actually find is that by working out the volume of gas that we're making in any given time, we can work out the rate of that particular reaction. And the more gas we're making in a given time, then the faster the rate of reaction actually is. There are a couple of ways that you can actually collect the gas, and this could be one of those practical questions. So one of the most basic ways of working this out is counting bubbles. Now, obviously, counting bubbles, you're likely to miss them. The bubbles are different volumes, and therefore a lot of problems there. We could have the upturned measuring cylinder that's filled with water and a delivery tube going in, because that will allow us to record the volume of gas there. But again, we've got issues in case the delivery tube comes out from under the measuring cylinder, or you're connecting bits up and so on. So the most accurate way to do this is by using a gas syringe. So if they've given you any way of recording the volume of a gas that's not a gas syringe, and they ask you for how you can improve it, use a gas syringe is your answer there. When we talk about those displacement reactions, as we've said, they occur with the halogens, but they will also occur with metals as well. So in our displacement reaction, a more reactive metal displaces the less reactive metal from its solution or its compound. So this is where you really want to have a little look at the reactivity series and make sure you've got a bit of an idea about where things fall. Obviously, things like potassium and sodium from our alkali metals, we know right at the top there. Whereas the things that we tend to have in jewelry, so silver, gold, platinum, they're right at the very bottom and they don't tend to do a whole lot. When we're actually looking at those displacement reactions, again, you need to be able to work out those half equations for them and identify whether it's oxidation or reduction. And again, we're just going back to those electrons again. So oxidation, loss of electrons; reduction, gain of electrons. And do remember that in any of those situations where we've got both a reduction and an oxidation happening at the same time, then we've got what's called a redox reaction, because both of them are occurring. Last thing we're really going to look at here are the useful patterns that we should know to do with the periodic table. So group 0 are the noble gases. They're not very reactive. Group 1 and 2 get more reactive the further down you go. Group 7, less reactive the further down you go. Groups 1 and 2 are both metals, and they are more reactive than the transition metals, which are in that block between group 2 and the other side. And then when we're talking about our metals, they can form the ionic compounds with the reactive non-metals. So again, this links back to the work we did for our paper 1. One of the things that they could throw in here, where we've talked about obviously making different gases, is how we can identify what gas we've actually made. So we need to know these different gas tests. The first one is carbon dioxide. Now, carbon dioxide is just using lime water. And lime water goes from colourless to cloudy. Okay, so if we've got carbon dioxide present, lime water, colourless to cloudy. Make sure you use the word colourless and not clear or anything like that, So colourless is the key phrase. If you were to say milky instead of cloudy, also perfectly acceptable there. Now, lime water itself is calcium hydroxide solution. And what we find is that when carbon dioxide reacts with calcium hydroxide, then we make water first of all, but then we also make calcium carbonate, which is the white precipitate, hence why it goes cloudy or milky. Now, the next gas they could ask you about is one of our halogens, which is chlorine. Now, chlorine is going to dissolve in water to form an acidic substance, but it also acts as a bleach. So that means it's going to change coloured substances to a colourless substance. So the test for chlorine is we have a bit of damp blue litmus paper, and it's damp because we put a drop of water on it. And then when you hold that above your test substance, it's going to go red first of all, because it's got an acidic substance come into contact with it, and then it's going to bleach it so it becomes white. So damp blue litmus paper goes red, then white, we've got chlorine. Third gas test is good old hydrogen. This is the one where we have a lit splint, put it in the tube, and it makes the squeaky pop sound. And the last gas test is good old oxygen, and that one is the glowing splint, put it in the tube, and it will then relight. So make sure you know those 4 different gas tests, because they could ask you how to identify any particular gas. The only other thing to really think about where we're talking about gases is when we're considering how you can actually smell something. And hopefully when you did any experiments, then you didn't just get a test tube, stick it under your nose and take a nice deep sniff, because that's going to end badly in a lot of cases. What you need to do is you actually hold your tube a little way apart, and then you do the royal wave and you waft it towards yourself, taking a cautious sniff. So if ever you're asked how you can actually sniff a gas safely, hold it away from you, waft the smell towards you, and then cautious sniffing is required. So that's all of C4 for the combined, folks. As I say, those you're doing triple, we're going to come back to the triple only bits at the end. So C5 is next for everyone. And the first bit is just for those of you doing the higher tier. So what we actually find then is we're going to think about the concentration of a solution to start off with. You've got to know a conversion here, because they could give you things in centimeters cubed and you're going to need it in decimeters cubed, or they could give you something that you might want to convert back to centimeters cubed. So if we're converting centimeters to decimeters cubed, we divide by 1,000. If you go the other way, it's multiplied by 1,000. So our first formula we need to know for our exam tomorrow is concentration. And there's 2 different ways we can look at this. So concentration could either be the mass in grams of our solute divided by the volume of solution in decimeters cubed, and that'll give us a concentration in grams per decimeter cubed, or we could work out the concentration in moles per dm cubed. And there all we do is the amount of the actual solute in moles divided by the volume of solution. So it's always an amount divided by the volume. Just double check to see whether it's a mass in grams or an amount in moles to give you the right units there. For everyone, so foundation and higher, we need to know about the rate of reaction. And this is a big part of this paper. So when we're thinking about rates of reaction, we're looking at how quickly either reactants are being used up or the products are being formed. And all we need to do to work out the rate of a reaction is the amount divided by the time. So one of the key things could be measuring volumes of gases. And as we've already said, we could use the upturned measuring cylinder or the improvement of the gas syringe to do this. And from that, they could give you a table of results where you can then be asked to plot the graph with the line of best fit. So remember, where you are plotting graphs, sharp pencil. So if you make a mistake, you can rub it out. If you do it in pen, there's no spare graph paper in there, folks. So sharp pencil, plot your points carefully, because they normally only give you somewhere between 1/2 to 1 of the small squares as your leeway. So do go careful with that. Once you've actually got your graph, then we can calculate the rate from it. So one of the more simple ways to do this is that they're going to ask you to calculate the rate between 0 and 30 seconds, for example. So all you do is you have a look and see 0 to 30 seconds, 30-second difference, how much the volume increased by in that time, and then you do the change in volume divided by the change in time. So that's the easy way to do it. They could also ask you to do it from a single point on the graph. These are slightly trickier. So if you've got your little rate graph like this, and they ask you to calculate the rate at 30 seconds, then what you need to do is obviously just calculate it at a single point on the graph. My line is absolutely terrible as a straight line today, so you need a ruler tomorrow as well. But what we need to do is we draw a tangent to the line. So if that's our 30 seconds, then we put our ruler across here, and you're going to get it so it's equal both above and below. So we've got a nice straight line here drawn with a ruler, not my bad hand-drawn one there. You then obviously draw your little triangle coming along, and then you can work out, still same thing, change in volume divided by the change in time. But you must have that straight line drawn across first of all. That's about as complicated as calculating the rates actually gets. One of the key things here is that they could ask you about rates of reaction as the assessed practical part, because obviously we had a little look at a range of different factors that affect the rate of a reaction. Now, the way we do this is pretty straightforward in most cases. So you're going to have your reactants, you measure them with a measuring cylinder to get the right volumes, obviously, and make sure that the volumes are the same in each test. And then when you mix them, you're going to start timing something to happen. And depending on what reaction is going to determine what it is we're timing. So one of the common ones is magnesium ribbon and acid, in which case we're timing how long it takes for the magnesium ribbon to disappear. Another common one is the hydrochloric acid and sodium thiosulfate, which is where you start off with two colorless solutions, and when you mix them, we make this yellow precipitate that makes it all cloudy so you can't see the crosses underneath. So just read the question and it will tell you a little bit about which chemicals we've got, and then you can apply that to obviously work out an appropriate actual technique. What we're going to do then is go through each of the different factors that can affect the rate of reaction. So first one is temperature. Hopefully we do know that if you increase the temperature, then we increase the rate of a reaction. And if they ask you to explain this, then all you need to do is say that as we increase the temperature, the particles gain kinetic energy, therefore they're moving faster, and the key phrase of all, there are more frequent successful collisions. Now, those 4 words, more frequent successful collisions, are going to be a repeating factor throughout all of these factors. So if ever you've got a rates of reaction question and you're in doubt about what to write, throw it in, okay? More frequent successful collisions, those are pretty much your explanation for everything. Just a little bit of detail around why there are more frequent successful collisions depending on which factor. So increase in temperature, particles gain kinetic energy, move faster, therefore more frequent successful collisions, and we've got a faster rate of reaction. What we then find is our second is concentration. Now, hopefully we do know that concentration is a measure of how much solute is dissolved in the solvent, and therefore a more concentrated solution has a greater mass of solute dissolved in the same volume of the actual solvent. So when we increase the concentration, the rate of reaction increases again, because in the higher concentrations, there are more frequent successful collisions because the particles are more crowded. So there's just a greater chance of the collisions occurring because there's more of those particles in the same volume. What we do find is that in these reactions, then the reaction is going to come to a stop when what the thing called the limiting reactant has been used up. Now, you can always see where that's been used up on a graph because it's where it plateaus, so levels out. When we're looking at those rates of reaction graphs, as soon as you get to the part of the graph where it levels off and goes horizontal here, then that's where the limiting reactant's been used up. We're not making any more gas, therefore that's the limiting reactant being used up. Now, what we find is that the amount of product we make is always going to be proportional to the amount of limiting reactant. So if you double the amount of your limiting reactant, you double the amount of product you make. If you halve it, you halve it. Third factor then is our pressure. So if we increase the pressure, then the particles become more crowded and therefore collide more frequently. So more frequent successful collisions leads to a faster rate of reaction again. Do remember when we talk about pressures, we're talking about gases in this case. So just remember that anytime we talk about pressure, then we're talking about a gas reaction. The last one is the actual particle size. So this one you probably did with marble chips and acid of different sizes. So when we break a material up into smaller pieces, the surface area actually increases. So if we're thinking about the difference between a big lump on its own and we grind it up into a powder, then what we find is the powder has the larger surface area than the single lump. When we increase the surface area, the rate of reaction increases. And that's because as the size of the lump decreases, the surface area to volume ratio increases, and then we've got more exposed particles, so there are more frequent successful collisions once more, leading to the faster rate of reaction. The very last thing that we could look at to do with rates of reaction is something called a catalyst. So a catalyst is just a substance that's going to increase the rate of a reaction, but is unchanged at the end. Now, if they ask you for a definition of catalyst for 2 marks, your first mark is for saying that it's a substance that increases the rate of reaction. Second mark is for saying that it's unchanged at the end of the reaction. And the catalysts that we use are always specific to a given reaction. And as we come on to the work we will do in C6, then what we find is we've got a few key examples that we need to remember there. What actually happens when we add a catalyst to our reaction mixture then is it's going to increase the rate of reaction. So what we actually find is it's giving an alternative reaction pathway that's got a lower activation energy. So when we're actually having the particles colliding, they're more likely to reach the activation energy and therefore have a reaction. And again, that ties back into the work we did in C3 about those reaction profiles and the activation energies. When we come on to the next section, which is reversible reactions, the key thing to remember here is the good old reversible reaction arrow. So it's the half arrow, half going each way. So if you see that, it means reversible reaction first of all. And the key thing about these reversible reactions is that the products can react together to form the original reactants. So the reaction can go both forwards and backwards. Hence why we've got half arrow that way, half arrow that way. And obviously they could give you any example of a reversible reaction in your actual exam paper, even with chemicals you've never heard of before. But as soon as you see a half arrow in each direction, reversible reaction. One of the things we need to understand then is something called a dynamic equilibrium. So what we're thinking about here, first of all, is something that's occurring in a closed system. So if they ask you any of the conditions you need for it to reach dynamic equilibrium, it needs to be in a closed system, first of all. And that just means that no substance can enter or leave it. So it could be as simple as having a flask with a stopper in the top. If we've got that reversible reaction taking place in a closed system, it will reach this dynamic equilibrium. And that's where the rate of the forward reaction is equal to the rate of the backwards reaction. So the concentrations of all of our reacting substances will remain constant. The reason we don't just call it an equilibrium and leave it there, the reason we have that word dynamic, is because the forward and backwards reactions are still occurring. So it's not just got to this static point and then everything has ended. We're constantly having the forwards and the backwards reactions happening, but they're happening at an equal rate, so the concentrations remain the same. For those of you doing the higher tier, you need to know about equilibrium position. Now, the equilibrium position is just a description of the relative amounts of the reactants and the products in that reaction mixture when it's at equilibrium. And what we find is if the equilibrium position is on the left, then the concentration of our reactants is greater than the concentration of products. If the equilibrium position is on the right, then the concentration of the reactants is less than the concentration of the products. And we can actually move that position by altering the conditions. And this is what we need to understand, still for higher tier only. So if we change the pressure, first of all, increasing the pressure will lead to the equilibrium position moving into the direction of the fewest moles of gas. So let me just give you a quick example here. If we've got our little reaction here, which is going to be, there we go, nice little reversible reaction. We know it's reversible because we've got our reversible reaction sign. Now, they're all gases. They would normally have the state symbols of G's. I just didn't write them. So what we've actually got, two molecules of sulfur dioxide, 1 molecule of oxygen, which means that on that side we have 3 moles of gas, and then on this side we've got 2 molecules of sulfur trioxide. So we've got 3 molecules of gas on this side and 2 on that side. So what we actually find then is, because we've got 3 moles of gas on the left, 2 moles of gas on the right, then increasing the pressure is going to move the equilibrium position to the right. So it's a way of making more sulfur trioxide in that case. Next one is the concentration. So if we increase the concentration of a substance, the equilibrium position moves in the direction away from that substance. So whatever you've increased the concentration of, then the equilibrium position moves away from that. Third one, temperature. If we increase the temperature of our reaction mixture, then the equilibrium position moves in the direction of the endothermic change. Now, hopefully we remember that exothermic reactions have a negative sign, endothermic reactions have a positive sign. And what they're going to do is they will give you a reaction with a reversible sign, and then on the far right, they're going to have a little sort of delta H and then a number. Now, if that number has a negative sign in front of it, then that tells you that it's an exothermic reaction in the forward direction. And therefore, the backwards reaction is endothermic. If it was obviously a positive sign, then it would tell you that the forward reaction is endothermic, backwards is exothermic. So you're looking for the sign there. When we increase the temperature, then it's going to move in the direction of the endothermic change. So as soon as you know whether it's forward or backwards as endothermic, you know whether it's going to be moving to the left or the right. Quick reminder for you then about those 3. Pressure, it moves towards the fewest moles of gas as we increase it. Increasing the concentration, it moves away from the substance with the increased concentration. And increasing the temperature, it goes in the direction of the endothermic reaction. So hopefully you can then apply that to any given scenario that they might want to throw in, because they could obviously give you any particular reversible reaction and ask you how you could increase the amount of the products made. So you then just have to look at the information given and apply those 3 principles to it. What we're going to come on to now then is C6 for everyone. So this is foundation, higher, combined, and the triples. And the first thing we're looking at are extracting metals. Hopefully we do remember that where we're talking about something called an ore, then that is a metal joined with something else. So it's like a rock or a mineral that we generally dig out of the ground. And it's got enough metal in it to make it economical to extract. So this is where we get a lot of our metals from, are ores that we've dug out of the ground. 3 key ones that we should really try and remember: malachite, which is copper carbonate; bauxite is aluminium oxide; and hematite is iron oxide. And what we're going to do is we're going to get these ores out of the ground, generally through a mining process, and then we've got to put it through some kind of a process to separate the metal from whatever it's joined to. So what we're going to then find is that the method we use to extract the metal does depend on its position in the reactivity series. So 2 key ways that we do this. Method 1 is electrolysis. It's an expensive process because it's using electricity, and we can use it to extract all metals. So that's the positive. Method 2 is where we're going to heat it with carbon or carbon monoxide. Big advantage, it's cheaper because we're not using vast amounts of electricity to do this, but it only works with metals that are less reactive than carbon. So it's not perfect. Hence why, depending on which metal we're looking at, you would have either electrolysis or heating it with one of our carbon compounds. So what we're actually going to come on to look at then is how we do this. And the first metal we're going to look at is copper. So when we want to extract copper from copper sulfide, we've got a 2-stage reaction. The first stage is where we get our copper sulfide and we do something called roasting it in air. So we've got our copper sulfide, we then pass oxygen through it with a lot of heat, and we then make copper oxide and sulfur dioxide. And then we take our copper oxide and heat it with carbon to make copper and carbon dioxide. And this is a good example of a redox reaction, and the carbon is acting as the reducing agent there. Another way we could extract our copper is by taking the copper oxide and reducing it by heating it with methane or with hydrogen. But again, that's looking at a more expensive process. Second metal we need to know about is extracting iron. Now, iron is going to be extracted using something called a blast furnace. And hopefully this little picture is familiar to you. So what we've actually got then is we're going to put everything in at the top up here. So that's going to be the coke, the limestone, and our iron ore. We're going to heat this up, hence why it's nice and hot at the bottom, and then it's going to get cooler as it goes further up. And then what's going to happen is we've got our liquid slag, first of all, which is the waste products, and our liquid iron that we can run off at the bottom. So that's the basis of what the blast furnace looks like. 3 raw materials we will add to it. First of all is the iron ore with hematite. Secondly is the coke. And thirdly is the limestone. So we add all of that to our blast furnace. And the first thing that happens is that the coke burns in that hot air, making carbon dioxide. So we take carbon, join it with oxygen, and make carbon dioxide. Stage 2 is the coke reducing the carbon dioxide to make carbon monoxide. So again, we've got carbon reacting with carbon dioxide to make carbon monoxide, CO. Stage 3 is where the carbon monoxide reduces the iron oxide to the iron. And this takes place at a really high temperature, about 1,500 degrees Celsius there. So we've got those 3 stages that are going to be occurring in order to get that liquid iron off at the bottom. The problem we have is that the liquid iron that we formed at that point would have a large number of impurities in it. So what we need to do is get rid of those impurities to avoid the properties of the iron actually being adversely affected. And we use the limestone to do this. So what we find is, as we've added the limestone to our blast furnace, the calcium carbonate, so limestone is, decomposes in a process called thermal decomposition. So it breaks down in heat to actually make calcium oxide and carbon dioxide. The second stage to this is that calcium oxide reacts with the silica, which is one of the key impurities there, to make calcium silicate. And that's what the slag actually is that we run off the top. So what we find is that the reason we can do that and separate the iron and the slag is that the slag is less dense than the iron, and therefore they form those 2 distinct layers, iron off at the bottom, slag off at the top. Third metal is aluminium then. So when we come to extract aluminium, then this is normally found in aluminium oxide. And we need to use electrolysis for this because aluminium is more reactive than carbon. The one massive problem we have with this is that aluminium oxide on its own has a very high melting point, over 2,000 degrees Celsius. So if we were going to heat it up to melt it to then carry out electrolysis at 2,000 odd degrees, that's going to cost us a lot of money. So what we actually do is we mix our aluminium oxide with this stuff called cryolite. And the whole idea behind that is that the cryolite will dissolve the aluminium oxide, and then electrolysis can take place at about 950 degrees Celsius, so much, much lower temperatures. What we then have is our electrolysis tank. So hopefully, again, a familiar diagram to you. So what we've got are carbon anodes, and we know they're anodes because they're positive. And we've also got our negative electrode that lines the tank, which is obviously the cathode. So we've got our anodes and our cathode, our 2 electrodes there. We've got our solution here, which is going to be our cryolite and our aluminium oxide dissolved. And then as it passes through the electricity through our solution, then we're going to end up with the aluminium, which will have a positive charge because it's a metal, being attracted to the negative electrode, the cathode, and then we can just run it off at the bottom. So what we've got there is the basis of electrolysis again. So what we've got is graphite, generally, is what we're going to use here as both our cathode and our anodes. So graphite is just a form of carbon. Hopefully we remember that. So that what we're going to see is that the oxygen we've separated from the aluminium. So we start with aluminium oxide. Aluminium is going to go to the cathode, and then the oxygen goes to the anode because oxygen has a negative charge, so it goes to the positive electrode. When it gets there, it actually reacts with the anodes, which are made of carbon, and it makes carbon dioxide. So we'll release carbon dioxide from the anodes, and get the aluminium at the cathode. But again, we've just separated out the aluminium, which is the key thing there. If you're doing the higher tier, then you do need to know those half equations again. So what we're actually going to find here is that our aluminium is going to be formed at the cathode with the aluminium ions, first of all, Al3+. They're going to gain 3 electrons to make the aluminium atoms. Whereas at the anode, what we're going to see is the reaction with our oxygen, and therefore what we're going to see here is our oxide ions, 2 of them, both with 2- charge, because oxygen is in group 6, therefore it forms a 2- charge on the ion, is then going to form oxygen gas, O2, and 4 electrons, 2 from each, remember. Therefore, if we've got 2 oxygens joining together, we will have 4 electrons overall. So they're your 2 half equations you need to know for the higher tier. Still, for folks doing the higher tier, we need to know about another process of extracting metals, which is biological metal extraction. Now, what we actually find here is it's using living things, hence biological. So the first thing here is considering the fact that in these abandoned mines that we've got, then they're quite prone to flooding. So what we actually see here is that in that scenario where our abandoned mines have flooded, then the metal sulfides become oxidized to make sulfuric acid. That acid then reacts with the metal ores, which creates these soluble metal compounds which get carried away in the water as it then drains from the mine. Now, the first process we're going to look at is something called bioleaching. Now, bioleaching is using bacteria here. So the bacteria oxidize the iron and sulfide ions, and we're going to get our sulfuric acid forming when the oxygen and water are present as a result. That sulfuric acid then breaks down the copper sulfide ores to release the copper ions. So we're using bacteria here to start off this process by oxidizing the iron and the sulfide ions. Then we get our sulfuric acid, which breaks down the copper sulfide ore to make the copper ions. Now, we've got a few advantages we should know about here. First of all, low-grade ores can be used, so we don't need these really high amounts of metal present. They can have very low amounts. It's quite cheap, so much cheaper than traditional mining and processing methods. The bacteria are naturally occurring and don't need any kind of special treatment, and it doesn't release sulfur dioxide into the atmosphere, which is always a good thing. In terms of the disadvantages, it's slow. We're relying on bacteria to carry out these processes. So it's quite a slow process, and we could make other toxic substances which aren't great. Still, just for the higher tier, then we also need to know about a process called Phyto Extraction, which is where we're using plants. Now, some of the plants that we can use here are really good at absorbing certain metal ions from the soil, and those metal ions then accumulate in the roots, shoots, and leaves of the plant itself. So what we do here is we pick one of these plants that's good at that, and we grow them in the soil that contains this low-grade ore or the waste from a mine. What we will find is those plants will then take up that metal into the plant itself so we can extract it. To help it out, what we do is we add something called a complexing agent. And that just means it makes it easier for the plants to absorb the metal ions from the soil. Once they've done that, the plants have grown, we harvest those plants, we burn the plants, and then we collect the ash, which actually has a high concentration of those metals. We can then extract the metal from that ash because we treat it as if it was a high-grade ore. Advantages of this one, it's cheaper than those traditional mining and processing methods. We've got much less waste being produced. There's smaller energy transfers involved, and it's pretty close to carbon neutral. So we're not increasing the amount of carbon dioxide in the atmosphere at all. Downsides though, we're talking about growing plants. That ain't quick. So it's a slow process. And obviously the crops may need replanting and harvesting for many years and many cycles before we've actually removed all of that metal from the soil itself. Back for everyone again, so foundation, higher, etc. Then we need to think about how we could choose certain materials. Now, I'm not going to go through this in much detail because pretty much what they're going to do is give you a table with various bits of information about different materials, and they're going to then say, select a material to carry out function X. So they could ask you to look at something like what polymer is best to make a cup for a hot drink. And in your table, you'll have things like melting points, maximum usable temperatures, and random other things as well. And all you need to do is look at the table, look at the actual use that they're asking you to pick the material for, and think what properties apply there. So all you need to do, look at the properties that you think apply, pick out the one that's got the best properties, and then back it up. If they ask you to compare the materials, then you've got to talk about each of the materials in the table, saying the advantages and disadvantages, and then give your final choice at the end. So do remember that not everything in the table is necessarily going to be relevant. So therefore, don't waste your time writing about everything. Pick out the properties that are relevant to that function. One of the things that you will need to consider when we're picking these materials is something called a life cycle assessment. And this is just a cradle-to-grave analysis of the impact of making, using, and disposing of any given manufactured product. So what we're going to be looking at here is information about the sustainability of it, the impact on the environment, the actual lifespan of the product that we've made, whether we can recycle it, and when we actually come to that disposal part of its life, how easily is it for us to actually decompose those materials, or are they going to persist for many, many years and release toxic byproducts? Once we carry out a life cycle assessment on any material, then what we do is we can look at the individual stages and pick out if there's something we could improve, or is there something else? If we can't improve it in any way, could we swap that material for something else that's better for the environment? Okay, so you just need to look at it and think critically about those. When we're thinking about that end stage and what we do with all of these products, all of this waste we generate in our everyday lives, we need to think about what we're going to do with it. And one of the key things is a lot of waste that we generate still ends up in landfills. So any of the rubbish you're throwing into your general rubbish bins at home, that's going to be going off to these giant landfill sites and just being covered over with some soil in the fullness of time. Now, that's not great. Obviously, these landfills are taking up a lot of space, not particularly nice to live near because they're quite smelly, and they attract an awful lot of vermin as well. So seagulls, rats, you name it, love it. So not great things, which is why we've got this big push on recycling. Now, recycling is really important to us because firstly, it's going to conserve these raw materials and energy resources. It's going to reduce the amount of harmful substances that we're releasing into our environment, and it reduces the amount of waste that we're chucking in these landfill sites. So where we can, we should really be looking to see if we can recycle. Now, when we come to thinking about recycling materials, it's not a case of everything can be recycled. So recycle the lot. We've got to think about a few different factors here as well. So firstly, how easy is it to collect and sort the waste? You probably have a range of different recycling materials that go into different bins or bags at home. So it's not a case of you've got one big bin for everything that could be recycled and off it goes to then be sorted somewhere else. We get you to do that first. So that's the first thing. Secondly, is we need to consider the amount and type of byproducts that are being released by the recycling process. We need to think about any energy that's involved at any stage in the process, and how much does it actually cost to recycle this material compared to disposing it of landfill or in incinerators where we're burning it. Once we've actually looked at all of this, then we'll decide what's worth recycling. And what we actually find is the process of recycling is relatively straightforward. We collect the materials, we sort the materials, and then depending on what it is, determines its actual process. So if it's a metal, we just melt it down, pour it into molds, and make these things called ingots, which are basically big slabs of metal that can then be taken off and used for other things. If it's paper, we mix it with water, we clean it, we roll it, and we heat it to make the recycled paper. Glass, melt it down and mold it into those new objects. And if it's a polymer, which are all these different types of plastics that we've got, we melt it down and we form it into new objects again. Do remember, though, that not all polymers can easily be recycled, hence why in your little recycling leaflet the council have sent you, there's certain things they don't want you to put in your recycling bin. Next thing we need to know about is our alkanes that come from crude oil. Hopefully, we do know that crude oil is a fossil fuel. So fossil fuels are made up of things that lived many millions of years ago. They died, they've become buried, and over millions of years, they've turned into this new substance. Now, in terms of crude oil, it was dead sea creatures. So things that lived in the sea millions of years ago died, sank down, buried, and they've turned into crude oil over millions of years. When we're talking about our fossil fuels, it's an example of a non-renewable resource. And remember, non-renewable is something that we are using up at a rate faster than it is being made. So they will run out. Other fossil fuels they could ask us about are obviously natural gas and coal. So what we find is, because we're using them up faster than they're being made, then they're what's called a finite resource. There's only a set amount in the world that we could potentially use. Any of those things, therefore, will potentially run out, some of them in your lifetime. So crude oil could potentially run out in your lifetime if we keep using it at the same rate that we currently are. And that obviously has a big impact because anything that comes from crude oil won't be there. One of the key things we need to understand then is this whole process of how we can get useful things from the crude oil itself. Because crude oil, when we get it out of the ground, is a mixture of hydrocarbons. And what we need to do is separate them into the individual hydrocarbons in a process called fractional distillation using this. So this is our fractionating column, which hopefully we remember. And what we find is at the very bottom down here, that's where it's hottest, and we've got a temperature gradient. So it's hottest at the bottom, and as you go further up, it gets cooler. So what we're using here is the idea that these different hydrocarbons in our crude oil have different boiling points. So that means they're going to get to a different level in our fractionating column before they're separated off. So what we find is that the more carbon atoms there are in that molecule, then the longer it is, the stronger the intermolecular forces, and therefore the higher the boiling point, because it's going to hold the molecules together more readily. What we'll find, therefore, is that at the very, very bottom of our fractionating column, so all the way down here, this is where we've got our longest hydrocarbons. So in this case, we've got bitumen coming off at the very bottom. Next up is the fuel oil. Then we've got our heating oils, then diesel, then paraffin, petrol, and then finally at the very, very top, we've got our LPG, which is the gas. So that one's got the lowest boiling point, comes off at the very top, highest boiling points at the very bottom. When we're actually looking at the molecules themselves of the hydrocarbon, then all of the atoms that make up the hydrocarbon are joined together by covalent bonds, because a hydrocarbon is something made of hydrogen and carbon only. So it's just hydrogen and carbon joined together. So what we then find is that all those hydrogen and carbon atoms are joined with a covalent bond, and the covalent bonds are much stronger than the intermolecular forces, the forces between the molecules. So when we actually heat it up, the intermolecular forces are being overcome, so therefore the molecules separate to form the vapor, but it's not enough energy to break apart the covalent bonds between the carbons and the hydrogens, so they stay as they are. Now, once we've gone through that whole process of fractional distillation and we've separated them out into all those individual fractions, then what we'll find is we don't have the right amounts for what we actually need. So when we're actually looking to see, do we have enough petrol coming out through fractional distillation? The answer is no. We've actually got a shortage of those particular fractions, but we have a surplus of some of the larger ones. So what we then find is that supply and demand are not being matched, which means that we then bring in a process called cracking. Cracking is where we're going to convert the large alkane molecules into smaller, more useful hydrocarbon molecules. So an alkane and an alkene that are smaller. We're breaking a big hydrocarbon into smaller ones. Now, in order to carry out this process of cracking, we need two things. We need a catalyst, which would usually be alumina or silica, and we need a high temperature, so 600 to 700 degrees Celsius there. Now, the whole purpose of doing this, I've said, is to then break these surplus large hydrocarbons into the shortage smaller hydrocarbons. So it's a way of matching supply and demand together. What we find is the reason that we've got a surplus of these large hydrocarbons is because they're not as useful as the smaller chains. They don't really flow easily, they're quite viscous, and they're pretty hard to ignite. So we can't just say, oh, we're just going to burn the big ones instead. Doesn't work. So what we're going to find is we will need that process of cracking to meet the demand that we actually have. Next little topic we're going on to for everyone then is the atmosphere. So one of the things we need to understand here is the entire history of Earth's atmosphere in pretty basic terms. So what we're going to see then is if we think about the age of the Earth, it's about 4.54 billion years old. It's quite old. And in the very early stages of our planet's development, then it was pretty much just volcanic activity here, there, and everywhere. So volcanoes erupting pretty much non-stop. And because we had a lot of volcanic activity, then we had this really high volume of water vapor and carbon dioxide being released to make our early atmosphere. As the Earth started to cool, then that water vapor condensed to form our early oceans. So that meant that the atmosphere we had then was made up of mainly carbon dioxide with small amounts of methane and ammonia. Bit later on in the Earth's development, then plants and algae evolved. Once plants and algae had evolved, then we have photosynthesis taking place. Hopefully we remember from our biology, photosynthesis is carbon dioxide being taken in by the plants and oxygen being released. So carbon dioxide plus water makes glucose and oxygen. So this means that from the point of our algae and our plants evolving, oxygen levels start to increase. Once we've actually got oxygen in the oceans, which is where these plants and algae were originating, then what we find is the oxygen reacts with the metal to make metal oxides. And then once most of that metal has been oxidized, that free oxygen accumulates in the atmosphere. So that leads us to eventually get to the atmosphere that we've got today. And you do need to know these percentages. So nitrogen, 78%, oxygen, 21%, and 0.04% is carbon dioxide. So what we've actually got there, those three gases you need to know, nitrogen 78, oxygen 21, carbon dioxide 0.04. They could give you a little pie chart and ask you to label those. So if you know the percentages, you can pick out which is which quite easily on there. Obviously, that would be our atmosphere if we as humans didn't come in and interfere with stuff in our usual way. So what we're actually finding then we need to consider is the impact of us as humans on the atmosphere. And one of the key ways we're going to do this is by creating a ton of pollution. So pollutants, quite simply, are any substance we're releasing into the environment that may harm living things. And one of the key ones is carbon monoxide. Now, hopefully you remember carbon monoxide is made during the incomplete combustion of fuels that contain carbon. And this is going to be taking place in any area where we don't have a good oxygen supply going in. So vehicle engines are a key one for this. We take the hydrocarbon, limited supply of oxygen, we make carbon monoxide, carbon and water. That carbon monoxide is a problem for living things, particularly us. You don't want to inhale large quantities of carbon monoxide because it binds to the hemoglobin in your red blood cells. If you've bound your carbon monoxide to it, then they can't carry oxygen. So if you breathe in too much carbon monoxide, you don't have the ability to transport enough oxygen, and therefore you're going to suffocate and die. Big problem with carbon monoxide is it's colorless, odorless, and tasteless, so we can't detect it easily. And you will start to notice certain symptoms if you are inhaling carbon monoxide. You're going to feel drowsy, you'll have difficulty breathing, you're going to get a headache, you'll feel a bit sick and get nauseous. And if you actually keep inhaling it, then death is the end result. So not a good thing to do. The second type of pollutant we need to concern ourselves with are particulates. Particulates are just small particles produced during the incomplete combustion or during certain industrial processes. Now, those small particulates are really problematic to us because if you breathe them in, then they can settle deep in your lungs. And this can then lead to a condition called bronchitis, which is basically where you get inflammation in your lungs, and it then can lead to breathing problems. So not good things to breathe in at that point. The next one we're going to consider are nitrogen reacting with oxygen. So when we've got nitrogen and oxygen, they don't normally react together, hence why our atmosphere is 78% nitrogen and 21% oxygen. But if we actually have high temperatures like we find in vehicle engines, then the nitrogen will react with oxygen to make nitrogen monoxide. That nitrogen monoxide is oxidized in air to make nitrogen dioxide, and together they're just known as the oxides of nitrogen. Now, these aren't good things to produce because they will dissolve in water vapor in our clouds in order to make acid rain. And acid rain, when it falls, is going to do things like eroding stonework, it can corrode metal, it kills trees, and if it actually is falling on areas like lakes and rivers, it can alter the pH to the point that it kills anything living in them. So acid rain, bad thing. If we then consider burning fossil fuels, another pollutant we'll make is sulfur dioxide. And this is from those impurities that we've got there. So things like sulfur, when it burns in oxygen, makes sulfur dioxide, and that's also going to cause acid rain. If you breathe sulfur dioxide in, again, you can get breathing difficulties. So all of these things that we're doing that are burning these fossil fuels are leading to problems not only for the atmosphere and the environment, but also for us as human beings. Hence why we're trying to reduce all these emissions. The last pollutant we're going to look at is carbon dioxide. Now, this is the one that we associate most closely with climate change. So what we're going to see then are we've got three greenhouse gases: carbon dioxide, methane, and water vapor. But the one we concern ourselves with is carbon dioxide because this is the one that we can actually reduce the amounts of most easily. When we're thinking about climate change, then, this is where we've increased the amount of these greenhouse gases within the atmosphere. And as a result of that, when the sun's radiation comes in, it's absorbed by the surface of the Earth. It then is re-radiated by the Earth's surface. And normally, a large proportion of that would pass back out into space. And so we'd stay at a pretty static temperature. If we've increased the amount of greenhouse gases in our atmosphere, they will absorb more of that infrared radiation and then re-emit it back to the surface of our planet, therefore leading to our increased temperatures. So what we're seeing here is an increase in the mean surface temperature of the Earth, which is what we're referring to when we talk about the enhanced greenhouse effect. It's basically how we as humans have led to the mean surface temperature of planet Earth increasing. Some of the things that we're doing to actually do this then, first of all, is actually the combustion of all these fossil fuels in cars, industry, and so on. And we've also got huge numbers of cattle for meeting the needs of our actual beef productions. So cattle produce lots of methane. That's bad news. The reason that we're quite concerned about this whole idea of climate change is because if that temperature of the planet is increasing, then we're more likely to see the ice caps melting, which we're seeing, which then leads to flooding. And in other areas, we could see things like droughts and extreme weather events, so more powerful hurricanes and so forth. Because of this, what we're actually going to do is reduce as many of these greenhouse emissions as we can. So a few basic things we can do here. We can reduce the consumption of fossil fuels, first of all. We can use more renewable energy sources as opposed to the non-renewables. And we can use these things called carbon capture techniques to stop the carbon dioxide we are making from getting out into the atmosphere. Obviously, that's not the only thing we can do. We can also have a little look against protecting from the effects of this climate change. So if we know sea levels are rising, we can put in better sea defences. We can bring in better flood barriers and flood defences if we know an area is prone to flooding. We could actually change buildings to withstand this extreme weather. So we can take those steps to just deal with the effects, but it's far better to obviously avoid it in the first instance. Next thing we need to know about then is drinking water, which is going to be the last thing for those of you doing combined science. And then we're going to go back over any of the triple concepts that we've jumped from the 4, 5, and 6 topics. So hopefully you know that water is kind of important for existence. You need to drink water to live. Still combined science at the moment. Now, what we find is that the water that you are getting from your taps has actually come originally from places like lakes, reservoirs, rivers. Any of those are fine answers. But from those, it could have a range of possible contaminants in it. So what we've actually got are things like leaves and soil, so these insoluble materials just floating around in it. You've got various soluble substances like salts and pollutants in there. And there are the potential for microorganisms too. None of which are good things to have in water that you're going to drink at the end of the day. And I'd hope that none of you are actually going to sit there and get some water out of a lake and drink it straight away. If you are, it's not going to end well in most cases. So what we're going to have to do is go through a series of processes in order to take that water and then produce what is the safe drinking water at the end that you can consume without worry. So what we're actually seeing is 4 stages. We've got filtration, first of all. That's going to remove any of these large objects. Second one is sedimentation, which is where things sink down to the bottom. Third is another filtration to remove small objects. And then finally, we have chlorination, which is all about killing the bacteria. So what you've probably seen is a diagram like this. So we start off with our water in the reservoir at the beginning, and it passes through our first filtration stage. So it goes through these grates, basically. They're going to remove any of the large objects. From there, it then goes into a settlement tank, and in that, what's going to happen is it's going to sit, and any of the heavy particles are going to sink down to the bottom, and we can just run the water off from there. We then add things like aluminium sulfate and lime to it, and that then makes things like clay stick together, and again, it sinks to the bottom, so we just run the water off. We then get to this one here, which is another tank which has got this layer of different kind of stones and sand and so on, so that as the water then filters down through it, any of the smaller particles that were left up here are then going to be filtered out. So that's our second filtration stage. Then we come down and we're going to add chlorine to the water, because chlorine is going to kill any bacteria present, and then off it goes to our houses. So filtration to remove large objects, sedimentation, soil sinks and the large bits sink down. We add the chemicals to then clump it together, more bits sink out. Another filtration to remove any of the small objects, and then chlorination to kill the bacteria. The last way that we can make drinking water, if we didn't want to go through that particular process, is we can make it from seawater. Now, seawater is obviously salt water, so you don't want to be drinking that straight away, otherwise it's going to kill you. And what we need to do is put it through a process of desalination. Now, that's going to remove the salts to make the water drinkable or potable. If we're doing this on a small scale, then it's using something called reverse osmosis, which is just a process of ultrafiltration that filters the salts out. If we're using large-scale desalination, then it's using simple distillation to do it. So for those of you who are doing combined science, that's it. We're done. That's everything you need to know. So the last thing that we need to do then is, for those of you doing triple science, we're going to go back over the bits from C4, C5 and C6 that we didn't cover because it's not in combined. So C4 for the triple science folks only. You also need to know about transition metals. So the first thing we should know about our transition metals are some of the physical properties. So what we find on the periodic table, you've got obviously the 2 sticky uppy bits at each end, and then there's a sort of lower block. That lower block are the transition metals between groups 2 and 3 on the periodic table. As the name transition metal suggests, they are all metals. It's not a trick. There's no weirdness here. Literally every single one of them is a metal. And they've got typical metal properties. So shiny when freshly cut, good conductors of electricity, they're going to be strong, they're going to be malleable. Any typical property of metal applies here. They could ask you to compare the transition metals and group 1 metals. And if we do that, then the transition metals are stronger, they're harder, have a higher density and higher melting point than the metals in group 1. In terms of the chemical properties, then the transition metals react really quite slowly, if they react at all. So this is where they're useful in things like jewelry and so on. Now, what we will find is that these transition metals have a little bit of complexity where we're talking about the chemical properties, because they don't just form a single ion. They can form more than one type of ion. And the way we know what type of ion it is and what the charge on it is because they're going to put a Roman numeral in brackets. So if it's iron with little 3 in brackets, then it's iron 3 oxide, okay? So let me just show you what I mean by the Roman numeral in brackets. So if we have this, then that tells us that the charge on the iron ions is going to be 3+. If it was only Fe2, so if it had the 2 in brackets, then the ions Fe2+. So whatever the Roman numeral is, tells you the charge on the ion for the transition metals. Now, one of the things that you need to be able to do is identify key metals from a set of results. Now, one of the ones that you would have done here are the flame tests. So this is where we're going to be identifying a metal ion by basically burning it. And the color of that flame is actually going to tell us what metal ion we have. So they could ask you how to carry out a flame test, in which case we get a nichrome wire loop and we're going to clean it by dipping it in concentrated hydrochloric acid and holding it in a raw and Bunsen flame until the color doesn't change. Once we've got it so the color's not changing with just the loop, you dip it in the test solution or make it damp with a bit of distilled water and dip it in the powder so the powder sticks. Then hold it in a roaring Bunsen flame and see what color it burns. This is where we need to know a whole bunch of colors, I'm afraid, folks, and there's no easy, quick way to learn it. You've just got to know them. So there are 5 colors we need to know for the flame tests. Lithium, first of all, is red, sodium is yellow, potassium is lilac, and then calcium is an orange-red color, and copper is a greeny-blue color. So those are the 5 colors you need to know as the flames. Now, what we're going to find is that they could ask you, what's a possible source of error in a flame test? And the simple answer is contamination. A roaring Bunsen flame is where you've got the air hole fully open, so the blue flame on the Bunsen you might have heard it referred to as. The second way that we can identify these metal ions is using something called the hydroxide precipitate test. Now, group 1 hydroxides are soluble in water, whereas most other metal hydroxides are insoluble in water. So because of that, we use sodium hydroxide in these experiments. So when we add our sodium hydroxide then to our solution that we don't know what metal is present, we make an insoluble solid, a precipitate. Depending on what color the precipitate is going to tell us what metal ion is actually present. So 5 colors again, I'm afraid, folks. Iron 2 will be a green precipitate. Iron 3 is an orange-brown precipitate. Copper is a blue precipitate. And then both calcium and zinc are white precipitates. Now, if they're being a little bit mean, they could tell you that there's 2 precipitates that are white and ask you what's what. And the way we identify that is by the extra information they give you. Because zinc hydroxide, so the white zinc precipitate there, that will dissolve and form a colorless solution if we add an excess, so a lot, of the sodium hydroxide. Whereas the calcium hydroxide, the other white precipitate, won't dissolve. So if they ask you how you could work out the difference between calcium hydroxide and zinc hydroxide, then you just add an excess of sodium hydroxide. The zinc hydroxide will dissolve and form a colorless solution. The calcium hydroxide will not dissolve. So just remember that side of it. The other thing we need to be able to do is identify the different anions. So what we find here is we've got a couple of different tests we need to know for the different anions. So the first one is testing for sulfate ions, the SO4 2-. The way we do this is we add a few drops of dilute hydrochloric acid first of all, and then we add a few drops of barium chloride solution. If we get a white precipitate forming, then we've got sulfate ions present. No white precipitate, no sulfate ions. Second test is for carbonate ions, CO3 2-. Again, we're going to add our hydrochloric acid, and if we get bubbles, we've got carbonate ions, because the bubbles of gas that we're making are carbon dioxide. And that's also why we add the hydrochloric acid to our initial test solution when we're going to go and add the barium chloride, is to remove any other impurities first of all. Third one is testing for the halide ions, so the ions in group 7. And what we're going to do here is add a few drops of the dilute nitric acid first of all, and that's just going to remove any other ions that are present. And then we add a few drops of silver nitrate solution. Now, the silver nitrate solution is going to form a different colour precipitate depending on which halide ion is present. So if it makes a white precipitate, it's chloride ions. If it's a cream precipitate, it's bromide. If it's a yellow precipitate, it's an iodide ion. So you need to remember, you get more colours. White is chloride, cream is bromide, yellow is iodide. Now, obviously we've gone through a range of different colours there and a range of different tests. They could give you a 6-mark question where you've got a table with different sort of samples, A, B, C, for example, and then they will have different results of those reactions. So you could have flame tests, you could have the hydroxide precipitate tests alongside various colours that we're making in terms of sulfates, carbonates, and so forth. And they could ask you to identify what chemicals are present in each of those solutions. So whatever you do on this one, even if you're not sure on every test, you should be able to pick up some marks. Because if you can look at it and think, oh, hold on, that one's burning with a green-blue flame, therefore it's got copper ions present in it. If you write that, that should be enough to get you the level 1 answer. So all you need to do is just sit there, have a little look at the table, and pick out the bits you know first of all, and just work along it in a logical order. So you can work out what metals are present, either from flame tests or the hydroxide precipitation reactions. And then obviously you can work out the other half of your salt from looking at whether you were testing for the halides, whether you were looking for carbonates or sulfates. And when you put that together, you can work out the name of whatever chemical you started with. Just take it in logical order and write down whatever you know, and you should get some marks, even if you don't get the whole lot. Next thing we need to know is about the instrumental methods of analysis. So basically, this is where we're using machines to work out what substances we've got. Now, the reason we're going to do this is because there's a few key advantages to us. First of all, it's very accurate. Secondly, it's really fast. And thirdly, they're very sensitive. So that means we can analyze really small amounts of samples. The first process you're going to know about here then is gas chromatography. So we talked about this back in our separating techniques in C2. So hopefully this is going to be a quick recap. What we do is we're going to take our sample and we turn it into a gas. We've got the carrier gas that then pushes it through that coil, which is packed full of those particles of the stationary phase. And the different size particles move at a different rate through there. As it moves past the detector, it then tells you how much of it is present. We then generate this, our chromatogram on the screen. So each of the little peaks is a different substance, and the height of the peak tells us how much of the substance is actually present. Now, what we actually have then is the reason we get the different peaks is because the retention time is different for each substance. Basically, that just tells us it's taken the substances a different length of time to move through that powder in that coiled section. So because they're going to be different sized particles, they move at a different rate, and therefore the detector picks them up at a different point. So we get the different peaks there. Now, the second technique we can use is something called mass spectrometry. And a mass spectrometer is going to measure the masses of atoms and molecules. So we can then use these to analyze the relative amounts of isotopes and work out the structure of actual molecules. So really quite a useful bit of kit. As the sample is put inside the mass spectrometer, then we ionize it. And that means that what we're going to do is form molecular ions. As those molecular ions gain energy, they can fragment, so they break into little pieces. When they pass through the machine, they're detected by the detector and it records the amount of each fragment there. And we get this thing called a mass spectrum. So we get the little peaks at the different points. And again, the height of those peaks tells us the relative amounts. If they ask you about the molecular ion, then it's always the one on the far right. So the one at the furthest right point, that is our molecular ion, okay? All of the ones to the left are where the molecule's been broken and made smaller fragments of it. So hopefully that's going to help you interpret those a little bit. Now, that's all of C4. Next, we're going on to C5 just for the GCSE chemistry, folks, remember. The first thing you need to know then is how we calculate percentage yield. And again, this is a formula you're going to have to know. They're not necessarily going to give this to you on the exam paper. So percentage yield is your actual yield divided by the theoretical yield times 100 to give you a percentage, hence percentage yield. So the way that we work this out then, 4 stages to it. First of all, calculate the relative formula masses. Secondly, we're going to calculate the sum of the relative formula masses using our balanced equation. So that's just your relative formula mass times the number of moles. Next, step 3 is we calculate the theoretical yield, which is your mass of limiting reactant divided by the sum of the relative formula masses for the reactant times the sum of the relative formula masses for the products. And then we just put those numbers into actual divided by theoretical times by 100, and you've got your percentage yield. What we're going to end up with then is a number between 0 and 100. Quick check, if you've not got a number between 0 and 100, you've gone wrong, double check it. Now, we don't often find that we have a percentage yield of 100%. It's not impossible, but it's not that common. So the reason that we won't have 100% yields is because of a few different factors. Firstly, and most commonly, we could lose some of the product. So if there's any way that products could escape, then we won't have 100% yield. The reaction may not go to completion, so there may be some of our reactants left over, hence not going to be 100%. Or we may find that reactants actually form other byproducts. The next calculation we need to do is atom economy. When we're talking about the atom economy, this is a measure of how many of the atoms from our reactants have made it to the desired product. So if we've got a low atom economy, then this tells us there's only a few atoms of our reactant ending up in the product that we actually wanted them to. If it's a high atom economy, then lots of them manage to make it into our desired product. So to work out your atom economy, it's the sum of your MRs of your desired product divided by the sum of the MR of all your products times 100. So nice and easy to do there, only to do with your products. Okay, so desired divided by all products times 100. The higher that atom economy of the process, the better it is for us. Because what we're going to find there is it's a more sustainable process because more of our reactants atoms are ending up in our desired product. For those of you doing the higher tier, you need to consider when we're choosing the conditions for a reaction pathway. So when we actually are trying to decide how to make a certain product, it's not a case of there's only one way to do it. Quite often in chemistry, we have a range of different ways that we can make the same chemical. So what we're going to do is have a little look and see which is going to be the best. And the factors we need to consider there, the yield, first of all, because we want it to be as high as possible. Atom economy, again, we want it to be as high as possible. Rate of reaction, we want it to be as fast as possible. Byproducts, as few as possible, because we don't want lots of byproducts unless they happen to be useful ones. And if it's a reversible reaction, how we could adjust that equilibrium position. So could we change the temperature and the pressure to get more of our product? So you need to consider those and then decide which is the best pathway. So they could very well give you a couple of different ways to make one product with those bits of information on them, and then ask you which is the best one to do. So again, you're weighing up the information they've given you to then select it. Still, just for the higher tier, we need to know about titration. So titration is the method that we're going to use to determine the concentration of an acid or an alkali through a neutralization reaction. And the key thing about these is they use something called a single indicator. We are not using universal indicator in a titration. You are only going to be using a single indicator like phenolphthalein because it gives a really clear endpoint for the reaction. So the way we carry out a titration then is you've got this thing called a burette, which is a big glass tube with graduations on it and a tap at the bottom. So you fill the burette with acid, first of all, and then we're going to use a volumetric pipette to transfer 25 centimeters cubed of our alkali to the conical flask. Now, the volumetric pipette is a nice, accurate pipette. It's better than a measuring cylinder because it's got a greater degree of accuracy. To our flask, we then add a few drops of our single indicator, give it a swirl so it's all nicely mixed. What we then do is we read the start volume of the burette, and we gradually add the acid from the burette to our flask, swirling as we do it to keep it mixed until we get that color change. Once that color changes, you record the end volume. So what we're actually going to end up with here then is something called a titer. So the titer is just the volume of acid we've used. And you're going to repeat this titration several times. Depending on how good you are at titrations will determine how many times you do this, because the idea is you repeat it until you've got something called concordant titers. So those are the ones within 0.1 centimeters cubed of each other. So obviously you don't just do it once and then that's it. You've got to do it several times, getting them within 0.1 centimeters cubed of each other for this accuracy. 3 indicators that we could potentially use in our titrations. Litmus, which is red in an acidic solution and blue in alkaline. Really obvious which one it is. Phenolphthalein, which is colorless in acidic solutions and pink in alkaline. And methyl orange, red in acidic, yellow in alkaline. And remember, we use those because it's a really clear change between the acidic and the alkaline. Not like universal indicator where you're kind of having a bit of a guess. Is it green? Is it blue? Is it greeny blue? No one really knows. So make sure you use a single indicator for these ones. One of the things that we would have to do is use something called a standard solution. So that's one where we've got a known accurate concentration. Because if we've got an unknown concentration that we're trying to work out, you need to be sure of the concentration of the other one. So to make your standard solution, you measure out 1 gram of your sodium hydroxide, for example, dissolve that in some water, and then you top it up to your 250 centimeters cubed in your volumetric flask. So you're just going to then give that a nice mix and you've got a known concentration of a solution. In terms of choosing the equipment in our titration, then we could use a measuring cylinder to measure the 25 centimeters cubed of our solution for the conical flask, but we tend not to because they are far less accurate than the volumetric pipette, hence that's what you should have used. We use a burette, obviously, and that's a glass tube which we're going to have on a clamp. Now, when you're actually using that, one of the things you need to do to be accurate is make sure it's perfectly vertical. If it's a weird slant, then it's not going to give you an accurate reading because obviously the actual meniscus, so where you've got the little dip at the top where the liquid comes to, is going to be across a few of those lines. So it must be clamped vertically for those accurate results. Things we can do to ensure we've got accurate results here is get to eye level with the bottom of the meniscus. So that means you're not just kind of glancing up and going, oh, it's roughly this. You're getting dead on with your eye level at the bottom of that meniscus. We record it to 2 decimal places so that if the bottom of the meniscus sits on the line, the second decimal place is a 0. If it's between 2 lines, then we put a 5 as the second decimal place. We've already mentioned the fact that we swirl the mixture constantly in order to mix it. Otherwise, what you'll find is it will change color. And then if you give it a mix, the color comes back again. So constant mixing to ensure that it's being spread throughout the whole solution. And as we get close to that end point, we add it a drop at a time. So you don't just turn the tap on, go and have a chat to your friends and come back a bit later and go, oh, look, it's changed. When it gets towards that end point, you literally add a single drop, you swirl, you see, add another drop, and so on. So drop by drop at the end means you're going to get an accurate result. What we then find that we can do, still just for the higher tier folks, is once we've got these titration results, we can carry out our titration calculations. So what we can actually do here is do this because we know three things. We know two reactants, we know the volume and concentration of one of those reactants, and the volume of the other. So we could be asked to calculate the unknown concentration. So the way we need to do this is by using one formula, which is the amount in moles is the concentration times volume. As long as you know that, then you can apply it to your titration calculations to work it out. So first thing you're going to do is write down amount in moles is concentration times volume. Now, do remember the volume is in decimeters cubed, and one of the things they do to add a little bit of complexity here is to give you it in centimeters cubed in the question. So make sure we convert. What we're going to do are 4 steps to work this out then. Step 1 is we're going to convert our volumes from centimeters to decimeters cubed, and we do that by dividing by 1,000. Secondly, we then calculate the amount of the reactant we know because we've got the volume and the concentration. So all we need to do then is concentration times the volume gives us the amount in moles. We then look at the balanced symbol equation, and then we're looking at the ratios. So we've obviously got the amount in moles of one of these, and we then just need to look at the other one from our balanced equation. From that, we can then apply this because we know how many moles of our other chemical we've got, and then put that back into our amount in moles is concentration times volume, rearrange it so that concentration is the amount in moles divided by volume, and then we've got the final concentration. So as long as you've got that one formula, you can work through those steps to get it. Last bit of C5 for those of you doing GCSE chemistry higher tier is the gas calculations. So another formula you need to know for this one, the volume in decimeters cubed is the amount in moles times 24. Remember, 24 for our gases. What we find is that 24 is important because 1 mole of any substance at all in the gas state will occupy the same volume at the same temperature and pressure. And that's what we refer to as the molar volume. And when we're talking about room temperature and room pressure, so RTP, as we refer to it as, then that is 24 decimeters cubed per mole. Hence why if we want to work out the volume of any amount of a gas, it's just the amount in moles times 24. Last thing we need to go through then is C6 for those of you doing GCSE chemistry. So this is for the foundation and higher tier folks first of all, and we're looking at fertilizers. Now, fertilizers are basically things we're going to use to make plants grow better. And what they're going to do is provide these things called essential elements. Now, essential elements are the elements that any plants require to grow. And there's 3 we should know: nitrogen, phosphorus, and potassium. If we don't have enough of those, then when plants grow, they're going to show certain deficiency symptoms. So if they don't have enough nitrogen, the plants don't grow well and they've got yellow leaves. If it's a lack of phosphorus, then their roots don't grow well and the leaves become discolored. Whereas if it's a lack of potassium, fruit doesn't grow well and they get discolored leaves. So if you're getting any of those deficiency symptoms, there's something lacking in the soil. Identify what it is and add fertilizer that contains it. Now, the key thing about fertilizers is they've got to be soluble in water. Plants cannot absorb a lump of solid through their roots. So they have to dissolve in the water and then be taken up through the roots of the plant first of all. So what we actually find is that these fertilizers we're using are soluble in water so that as it's watered or it rains, they dissolve and then the plants take them up with those required elements. One of the key ways that we're going to make the chemicals required for these fertilizers is in the Haber process. Now, this should be a familiar little diagram to you. So what we've got is 2 gases coming in, nitrogen and hydrogen. We then increase the pressure of them, put them into an area where we've got a high temperature and some catalysts, and it then makes ammonia, which we can condense as it passes over the cooling area, run off the ammonia, and recycle any of the unused gases. Now, what we see here is that the raw materials for the Haber process are air, natural gas, and steam, 3 raw materials. The nitrogen is going to be coming from the fractional distillation of liquefied air, and the hydrogen is made by reacting the natural gas with the steam, hence the 3 raw materials. And what we then make is ammonia, NH3. So we start off with nitrogen, N2, and hydrogen, H2, and we make NH3. And this is a reversible reaction. So what we need to be able to do from that then is we need to look and see what fertilizers we can make. This is going to give us ammonia, but that's not the only chemical that goes into our fertilizer. Because what we're really going to do is we're going to carry out a neutralization reaction, which is going to be an acid plus an alkali, making a salt and water. You need to be able to name that salt. There's 2 ways they could ask this. They could give you the name of an acid, the name of an alkali, and ask you what salt it is. Or they could give you the salt name and ask you what acid and alkali you would need to use to make it. As long as you know how salt names are made, then you should be able to work this out quite easily. So in our salt name, the first word is always going to be the name of the metal from the alkali, and the second word is going to be coming from the acid. So what we actually find then is sulfuric acid makes a sulfate, hydrochloric acid makes a chloride, nitric acid makes a nitrate, and phosphoric acid makes a phosphate. So as long as you know those 2 bits of information, you can work it out each and every time. When we come to consider how to make chemicals then, we've got 2 possible options. We could either carry out batch process or continuous process. So if we're looking at a process where we need large amounts of a chemical, like fertilizers, that tends to be where we're using continuous process, because this is making vast quantities. And as that name suggests, it happens all the time. Whereas if we're making smaller quantities of more specialist chemicals, that's where the batch process comes in. And again, this could be one of those scenarios where they ask you how you would make a particular chemical. So this is where you need to understand those key features of batch and continuous to be able to identify which one is going to be better. So for batch process, that one's got a low rate of production, a low cost of equipment, it's got large numbers of workers needed, so it's quite costly, and it has frequent shutdown periods. Whereas for the continuous process, it's got a high rate of production, a high cost of the equipment, only needs a few workers, so your manpower is going to be cheaper, and it's got much rarer shutdown periods. So you should be able to justify which one to use for any given scenario there. Now, if we go back to the idea of the Haber process, for those of you doing the higher tier, then we need to know about the conditions that we are choosing. So once we've got our little setup here, we did mention we increase the pressure over here, and this area we've got high temperature and we've got these beds of catalyst. So what we actually find then is you need to know a little bit more about the specifics. The temperature is 450 degrees Celsius, it's 200 atmospheres of pressure, and an ion catalyst. So those are the 3 conditions for the Haber process. The reason we pick those is to give us a yield of about 30%. Now that doesn't sound great, but it's all to do with balancing the cost of getting those conditions with the actual outcome from changing them. Because this is a reversible reaction, we're just going back to the work we talked about earlier in this, where we're looking at changing pressure, changing temperature, and so on, and the effect on the equilibrium position. So the reason that we've got 450 degrees Celsius is that it's the balance between a high enough temperature for a fast rate, but a low enough temperature to get us a good yield. And quite often, they're going to give you this graph. So we've got the different lines for the different temperatures, so 200, 300, 400, 500 degrees Celsius. And then along the bottom, we've got the pressure. And obviously the height here is our yield. So you might think, well, quite clearly what we want to do is have it only 200 degrees Celsius because that line goes the highest, but that's going to be happening at a much slower rate. So we take our balance of the 450 because it's a fast rate of reaction and still a reasonable yield there. In terms of the pressure, the reason that we've picked 200 atmospheres is because what we see here is that increasing the pressure is going to move the equilibrium position to the right. Now, what we find is we're not going to increase the pressure endlessly because increasing pressure requires quite specialist equipment to withstand high pressures. Specialist equipment is expensive. So we go to 200 because it's going to increase our yield to a certain extent, but not be too costly in terms of the equipment. The last thing we do is we're going to recycle any of the unused gases in order just to reduce that cost of obviously new raw materials. For the higher tier folks only, you need to know about something called the contact process. So this is how we make sulfuric acid. So raw materials are sulfur, air, and water. Three-stage process that we've got here. Stage 1 is sulfur burning in air to make sulfur dioxide. Stage 2, sulfur dioxide and oxygen react to make the sulfur trioxide. It's a reversible reaction, so the conditions we choose are 2 atmospheres of pressure, 450 degrees Celsius, and a vanadium oxide catalyst. And then stage 3 is where the sulfur trioxide is converted to the sulfuric acid by adding water. Now that third stage is really exothermic, so we don't carry out as a single step after all. We split it into 2. So the sulfur trioxide is passed through concentrated sulfuric acid to make oleum, and then the oleum is added to water to make a large volume of the sulfuric acid. So again, that one is one where we've got a reversible reaction, so equilibrium position could be brought in. Think back to applying those same principles again. The next process is making ethanol, still just for the higher tier folks. What we actually find is that when we're making ethanol, we can carry this out in a renewable process, which is using plants, because plants, as soon as we've used them, we can grow them again, they don't run out. This is using a fermentation reaction with yeast. So yeast contain enzymes that will convert glucose into carbon dioxide and ethanol. So if they ask you to write the word equation for this, it's just glucose makes carbon dioxide plus ethanol. And that glucose is coming from the plants itself. So plants plus yeast is going to make our ethanol. This one, we do need to think about conditions. Obviously, temperature is important because it's an enzyme-controlled reaction. So increasing the temperature initially will increase the rate of reaction because there'll be more frequent successful collisions. But because it's an enzyme, if you go too high, the enzymes become denatured and therefore it's going to bring that reaction to an end. What we normally do is carry this out about 35 degrees Celsius because that one is fast enough to actually have the reaction happening quickly, but won't denature the enzymes. Second option for making ethanol is a non-renewable raw material, which is using ethene, which comes from crude oil. So obviously non-renewable because crude oil, as we know, is a fossil fuel, therefore it's going to run out at some point. With that ethene, what we do is we hydrate it to make the ethanol. So we react it with water in the form of steam, which then takes the ethene and converts it to ethanol. 3 different conditions we need: 300 degrees Celsius, 60 atmospheres of pressure, and a catalyst of phosphoric acid. What we do need to be able to do then between those 2 processes is pick which one is best. So make sure you can talk about what the advantages and disadvantages are of those 2 processes. Back for everyone again, so higher and foundation folks, we need to know about alloys. So an alloy is a mixture of 2 or more elements where at least one of them is a metal. So there are 5 key alloys you should know about. Steel, which is main metal, is iron. Solder, which is made from tin and copper. Brass is copper and zinc. Bronze, copper and tin. And duralumin, which is the aluminium and the copper. So make sure you do know what they're used for as well. The reason that we have an alloy rather than just one of those metals on their own is because by putting more than one of those elements together, we've changed the properties and made it more useful to us. So just think about how we can modify those different properties by mixing. Good example here is solder, for example. And what we find is that's going to melt at a really low temperature. So normally metals have a high temperature to melt them, whereas by having our solder, which is the mixture of the tin and the copper, then it's got a much lower temperature to melt it, and therefore we can join electrical components together without damaging them. If we're thinking about something like bronze, for example, then the reason we'd use bronze rather than copper on its own is because it's stronger and harder. Because where we've got two different sized atoms, they don't slide over each other so easily. So again, just apply that to the right setting. The next thing is corrosion. So corrosion is where our metal is going to react with substances in the surroundings. Now, what we're going to find is different metals have different reactivities here. So what we actually find is that if we've got a metal that's unreactive, that's going to be useful in things that come into contact with water quite frequently. So this is why we use gold, silver, platinum in jewelry, because it's not going to react with water when you wash your hands, for example. One metal that will react with the oxygen and the water in the surroundings, albeit slowly, it does still react, is iron. So what we actually find is rusting is where we've got iron reacting with the oxygen and the water to make hydrated iron 3 oxide. Now, rusting is a redox reaction, and they could ask you about an experiment to investigate rusting here. So you'd have your different test tubes with your nails in there, and you'd adjust the conditions. So you'd have one with just water, you'd have one with just air, you could have one with the anhydrous calcium chloride, which is going to remove any of the moisture. You would have one with boiled water, because that one's got water but no air, and then you'd have a look at the results over a relatively long period of time. Obviously, the one that's got the most rust is the one that's most affected by those conditions. In terms of whether you need to know the symbol equation, then word equation should be enough here. But to be honest, even if they ask you to write a balanced symbol equation, because you obviously know oxygen is O2, water is H2O, iron is Fe, you can then work out the rest of it from that. So that shouldn't be too much of a challenge. The word equation is iron plus oxygen plus water makes hydrated iron 3 oxide. Now, we don't want things to rust generally. We use iron in a lot of things outside. So what we can do is take a few different steps to then reduce the corrosion. Might be as simple as painting things, because that then stops things coming into contact with the metal. If it's a moving object, we don't paint them. We coat it with oil or grease, or we could carry out plating either with zinc or tin. For those of you doing the higher tier, you need to know the little bit more about rusting in terms of what's happening with that equation. So what we actually have then is we start off with our iron, which is Fe, and it's going to make our Fe3 plus ions and 3 electrons. So if they ask you to write your ionic equation, then we've got iron atoms making the iron ions and 3 electrons. What we will find then is that the more reactive a metal is, the more easily it's going to lose electrons. Therefore, the more readily it will be oxidized. Back for everyone, foundation and higher folks, there is something we can do called sacrificial protection, which is all about using a metal that's more reactive than the one we're trying to protect. So quite often we'll get blocks of magnesium and attach them onto the hull of the ship, for example. Because the magnesium is more reactive than the metal making the ship, then it will corrode before the ship does. So that's just one way that we can carry out this sacrificial protection, because we're sacrificing the more reactive metal for the less reactive one. We could also do a process called metal plating, which is where we're going to actually coat the metal that we're protecting with another metal. And that's just going to stop air and water from reaching it. Obviously, different materials we can use for that. We could use zinc in a process called galvanizing, or we could use tin in tin plating. And all we're going to do there is that's what we use in our like food cans. So it's tin plated. The downside of that is that tin is less reactive than iron. So if we get a scratch or some kind of damage on that tin plating, then the iron is going to actually corrode really quickly because it then goes into the sacrificial protection mode. I'm not actually going to go into much detail on the different materials because, again, that's looking at properties and just selecting which one's best for a certain function. One type of material we could be asked about, though, are composite materials, which are made from two or more materials with different properties being combined together. So the properties of that composite material are different from those of the materials it contains. So that would be something like fiberglass, for example, where we've got those glass fibers embedded in a resin, and that makes it much stronger than on their own. Next bit is the organic chemistry bit that a lot of you really don't like. So the first bit of organic chemistry is looking at alkanes. So alkanes are a kind of hydrocarbon, and hydrocarbons are made of hydrogen and carbon only. So alkanes then form what's called an homologous series because they've got certain features in common. They've got the same general formula, first of all, and they are all saturated. So they've only got single bonds between all of those carbon and hydrogen atoms. You do need to be able to name the first four and draw the displayed formulas of them. So the naming part, the first bit of the actual name comes from the number of carbon atoms. So if you've got one carbon atom, it's meth, M-E-T-H. 2 is eth, 3 prop, 4 bute. So that gives you the first part of the name, and the ending just comes from what type of chemical it is. If they're alkanes, they all end in ane. So if we had a 3 carbon atom, alkane, then it would be propane. The general formula for these ones then, again, this is something that we hopefully already know, is quite simply CnH2n plus 2. So as soon as you know how many carbon atoms there are, change the n for that, times it by 2 and add 2 onto it to get your hydrogen. So that's going to give you the formula of any alkane. With the alkanes, what we find is we've got two types of combustion, complete or incomplete combustion. Complete combustion, plenty of oxygen, and therefore it's complete oxidation. We're only going to make carbon dioxide and water. If it's incomplete combustion, there's insufficient oxygen present, so we make carbon monoxide, and water in that case. The second one we're going to have a look at are the alkenes. So alkenes are another homologous series, so they've got the same general formula again. And the general formula for our alkenes is just CnH2n. Now, all of the alkenes are unsaturated because they contain at least one double bond. They will still undergo complete and incomplete combustion with the same product as the alkanes, but we need to know something called a functional group for them. Now, a functional group, quite simply, are the atoms, groups of atoms, or types of bond responsible for the characteristic reactions of the substance. And in the case of the alkenes, the functional group is the C double bond C. Now, what we'll find, because we've got a double bond, then alkenes can undergo addition reactions because that double bond can be broken and therefore they can join end to end to make a lot of polymers. One way we can test if we've got an alkane or an alkene is by using bromine water. So what we do is we've got unknown chemical, you add bromine water to it, give it a little shake, and if we've actually got it changing from the orange-brown colour to colourless, then we have an alkene. If it stays orange-brown, it's an alkane because it's not been able to undergo that addition reaction. The third one we need to know about then are alcohols. So another homologous series here, their general formula is CnH2n plus 1 OH, and all of their names end in ol. The functional group for this one is the hydroxyl group, okay, so OH. So hydroxyl group is the functional group for the alcohols. If we burn them in oxygen, then we're going to produce carbon dioxide and water when it's complete combustion, or incomplete combustion is going to be water vapor, carbon monoxide, and carbon. And yes, the only difference between alkane and alkene formulas is the +2 at the end. With the alcohols then, we can oxidize these to form carboxylic acids, which are the fourth and final group we're going to look at. So in terms of our carboxylic acids then, their functional group is COOH, which is the carboxyl group, and all of their names end in anoic acid. So their general formula is CnH2n+1 COOH. Now, do go careful with these because one of the carbons is actually in the functional group. So if they give you something like pentanoic acid, which has got obviously 5 carbons because it's pent, then you'd have C4H9COOH because there's 5 carbons in total, one of them being in the functional group there. If we've got our carboxylic acids, then these, as we've said, can be made by our alcohols reacting with an oxidizing agent, such as potassium manganate. So we could start off with ethanol and use it to make ethanoic acid. So the way we do that is we'd have our ethanol, we'd add potassium manganate and sulfuric acid, we'd warm it gently, and then what we'd find is we would end up with ethanoic acid at the end. So the reason we could see this reaction taking place is the manganate ions are purple and they become reduced to manganese ions, which are pink. So we can see that reaction taking place there. When we're thinking about the carboxylic acids, these are examples of weak acids. So because they are acids, they will have typical acid reactions. So they'll react with a metal to produce a salt and hydrogen. They'll react with alkalis and bases to make a salt and water. And they'll react with carbonates to produce a salt, water, and carbon dioxide, behaving the same way as any other acid we've looked at. The key thing to remember here is that the name of the salt that we make from a carboxylic acid reaction will have the ending OATE. So if we had ethanoic acid and sodium carbonate, then the salt would be sodium ethanoate. So it's that key ending there. Next bit are the polymers. So the first type of polymer are the addition polymers, and this is a good example of a lot of plastics. So hopefully we know a polymer is made from many monomers being joined together end to end, and the monomers tend to be alkenes. So they're undergoing an addition reaction because they're just joining together, they're being added on. And the reason that we have alkenes for this is they've got that functional group of the C double bond C, so the double bond can be broken and therefore join end to end with others. To actually carry out addition polymerization, we need a high pressure and a catalyst. And hopefully you remember to write the name of a polymer, just stick the word poly in front of the actual monomer name. And if you're working out the name of the monomer from the polymer, just write whatever's in the brackets. The next kind of polymers are the biological polymers. So this is a bit of an overlap with your biology course here. So we've got DNA, first of all, which is made from the nucleotide monomers. And hopefully we do remember that each nucleotide is made of a phosphate, deoxyribose sugar, and a base. The 4 bases, adenine, thymine, cytosine, and guanine, so A, T, C, and G. And then what we find in DNA is we've got those 2 strands in the double helix with hydrogen bonds between the bases holding them together. Second biological polymer is protein, which is made from the monomers of the amino acids. Third one, the carbohydrates, which are obviously made from simple sugars being joined together as those monomers. And those are all of the biological polymers you need to know. If you're doing the higher tier, you need to know about condensation polymers as well. Condensation polymers form in a condensation reaction, where 2 molecules are reacting together to form one larger molecule and one smaller molecule, which is often water, hence condensation being associated with water quite frequently. So we could start off with carboxylic acid and an alcohol, and we'd make an ester and water. So that's an example of our condensation reaction there. Now, our condensation polymers being made through these condensation reactions have different conditions to the addition polymers. They do not require a catalyst, and they will often occur at room temperature and room pressure. But the monomers for the condensation polymer require two functional groups. So one of the ones that we had a little look at are amino acids in order to make our proteins, and they've got two functional groups. Your amino acid has an amino group, which is NH2, and a carboxyl group, the COOH. So they're the two functional groups, and therefore they can join on. Now, what we actually find is, as those monomers join by those two functional groups, then they're joined by something called an amide group, so CONH. In terms of examples of these then, we've got polyester, which is an artificial condensation polymer made from carboxylic acid, which has two carboxyl groups, and alcohol with the two hydroxyl groups. So what we're going to find here then is that they will form many ester groups when they join together, hence polyester. Poly, many, ester is the kind of group we're joining. Now, these are the ones that we're going to find in a lot of clothing. Second example is polyamide, another artificial condensation polymer made from carboxylic acid and amine. So these ones are going to form many amide groups, hence polyamide. And a good example of that is nylon, again used in clothing quite frequently. The very last thing we need to all do is for foundation and higher tier folks, which is having a look at how we can actually make electricity using chemistry. So it's the fuel cells. So if we think about a chemical cell, they have an exothermic reaction within the cell that then develops a potential difference between the two ends of it. So that when we connect that cell into a circuit, current's going to flow through the cell and those circuit components. The fuel cell then is going to produce electricity through a chemical reaction between a fuel and oxygen, but there's no combustion, so we're not burning anything. And that's really important because fuel cells are used in things like the space shuttle. Now, burning stuff in space is a bad plan because if you have a fire on a space shuttle, you can't just leave and go somewhere else. So we need to generate electricity without burning stuff, hence fuel cells are used. And what we're actually doing is we're going to have hydrogen reacting with oxygen. And what we're going to make then is water vapor. So what we're going to see is a setup with this. So this is our fuel cell then. So we've got hydrogen and we've got oxygen coming in. Down the center here, we've got something called a proton exchange membrane. And we've got an electrical circuit running across the top here. So what's actually going to happen in our fuel cell then is the hydrogen molecules lose electrons to become hydrogen ions, first of all. Those hydrogen ions are then going to cross through the proton exchange membrane to the other side of our fuel cell, and the electrons move through the external circuit to the other side of the fuel cell. Once we're on the other side, the hydrogen ions combine with oxygen and the electrons to make the water vapor. So the only byproduct here is water, which can obviously then be used in space for drinking, which is quite useful. So in terms of the advantages of our fuel cells, they're lightweight, they're compact, they've got no moving parts, there's no combustion, there's no carbon dioxide emissions, and we're only making water as the waste product, which we can then drink. Disadvantages, though, is that most of the hydrogen that we currently have is made through the use of fossil fuels. So that's a downside, obviously, because anytime we're using fossil fuels, then we do have the other downside of they will run out and other pollutants. And finally, the catalysts that we're using in our fuel cells are actually quite poisonous and therefore have to be disposed of very safely at the end of the fuel cell's life. That's everything. So overran by 10 minutes again. Seems to always be just 10 minutes over the 2 hours this year. So when you are in the exam tomorrow, do make sure you read the questions carefully. Anytime they're giving you tables of information and asking you to select something, then do justify your choices using the information from the table. But don't just focus and say, I would use this because of these 3 reasons. Make sure you compare it to the others and say, well, you know, that one we won't use because that's rubbish. So do read the information they give you, because quite often they give you a fair amount in the actual question. If you're being asked to identify chemicals from chemical reactions, even if you don't know the final everythings, put something that you do know, because you can always pick out something you know to get to at least a level 1 answer. Hopefully that's been useful to you tonight, and it looks like people in the chat have been much more sensible tonight. So we will have the chat running on the physics live stream on Thursday night, which will be again at 6 o'clock. So make sure that you read the questions carefully, attempt everything, don't leave blank spaces, because as much as I as a marker do love the blank spaces, because I can just hit a blank page button and skip quick and get more money, it's not going to help you get a grade. At least have a guess, because you might be lucky. And then join us again for our live stream on Thursday. So good luck to